Welcome to the second lecture on deep learning for natural language processing. My name is Ivan Habernal, and today we'll be talking about some very basics of machine learning and some principles that are required for you to understand for actually making deep learning or machine learning work for some tasks. So, for example, how to evaluate our tasks, what are different loss functions, how can we make sure that our models generalize, and how can we evaluate this generalization, and so on. Before we jump on that, though, we need to understand a little bit of notation. And here comes the thing. So, for example, when we talk about vectors in linear algebra, we typically talk about column vectors. So if you remember your linear algebra, we have column vectors and they look like that. And when we talk about vectors in deep learning, we might think as a row vector, and so which are in linear algebra terms column vector transposed. So this is not anymore an object in R3 space, but could be seen as a matrix from one row and 3 columns. But why is it helpful for us as a computer scientist? Because we work with lists and arrays, and array is just a list of numbers. Two-dimensional array could be something like matrix. If you come to more dimensions, it gets complicated. So it's important to see, depending on the context, what we mean by vector, because sometimes the equations in the mathematical equations might be contradicting to what we are actually computing then, and it's better to double check. Excuse me. Another point is that when we work with Numpy, for example, we have another thing called broadcasting, which makes it even more complicated, because in broadcasting we can mix up different so-called shapes or dimensions of our multi-dimensional arrays, and then vectors, matrices, tensors get very messy. So what I suggest first is to have a look at Numpy broadcasting and to understand what it means, because it will be used later on. And also to be cautious when we talk about vectors and multiplying vectors and matrices, to know sometimes it could be column vector, sometimes it could be row vector, so better pay attention. For matrices, we'll be using bold uppercase letters, so this is standard matrix as we know from linear algebra. 2 rows and 3 columns, so 2 times 3, and they are indexed like that. Scalars, simple number, we will be using lowercase letters, for example. A and B and C are real numbers here. So here is no surprise. We will be using dot, and dot can also already mean different things. So depending on the context, it could be simple scalar multiplication, like A and B. 2 times 3 is something, so real times real is a real. It might be a dot product of 2 vectors, and the dot product of 2 vectors is their summation over all indices. So for all positions of the vector times the other. So dot product, and then what is coming out is again a real number, but the input is n-dimensional vector or 2 vectors. We will use dot also sometimes for matrix vector or vector matrix multiplication. So x times w or y times z. And matrix multiplication is something where you need to take care of the dimensions. So that if you do matrix multiplication, we might be using also some other times, but here it's the input matrix is m rows times n columns, and these two inner dimensions, they have to match, and what you get is the m times p, so linear algebra basically. There will be some calculus involved as well, and we'll be derivating functions. We might see in derivations with this of function f as f prime in physics, and we'll be denoting them by df over dx. So this will be our notation for derivations. And if we have a function of multivariate function of several variables, well, such as here fx1 as xn, we'll be using this for partial derivatives. So this will be partial derivative of function f with respect to variable xi. And then we will have a gradient, so-called total derivative, which will be our vector, a row vector of partial derivatives. So this symbol is called nabla. So nabla f is a row of partial derivatives to each variables of this function f. And again, multiplication vector matrix. So here's an example. Let's go through. So if we have vector x time matrix w, and x is a row vector, and w is a matrix n times d, what will be the output? So let's start with x. So let's x be some vector like that. So length will be n, and then w is n rows times d. Then we'll be taking for each column multiply by x, and we will get an output of dimension d. So again, and the inner dimension have to match, and we will get 1 times d. So this will be matrix 1 times d, which we can consider as a row vector of dimension d. Cosine similarity, also helpful in machine learning, is the similarity of two vectors, and it's computed as follows. So we take the dot product and we normalize it by the product of their of the norms. So L2 norm. So this is Euclidean norm, or L2 norm, and this is a square root of the square of all the items, and we multiply them together. So the similarity is in interval 0 to 1, the cosine similarity. And we have already one function that is applied element-wise to vectors, and it was the activation function. So some functions are applied on each element of vector x. If there are other examples of confusing mathematics, I'll get back to them when we reach the point. But now let's go to supervised machine learning basics. So let's describe the problem in detail. Let's have n labeled data points, or we can call that examples, depending on terminology. So for example, in Google terminology, they call it example. We can call it instances or data points. I have to say example sounds actually very logic, because we are showing examples of some problem and we're learning from examples. As humans, we also learn from examples, not from instances or data points necessarily. And these examples is a set of tuples. And the tuple is the input representation on the feature vector, and the y is the true label or God label of the x, and we have a set of them. So these are our this is our data set. Then we have a model, and the model is parameterized by some parameters. For us, general parameters is just a vector of theta, and the model outputs some value, which we typically use the y hat. So this is our model as a function. It takes some input, feature vector x, then it's parameterized by the theta, and it outputs a y hat. And the last here in this collection is the loss function. And the loss function is some sort of function telling us how far off or how good our model, parameterized by theta, is performing on the labeled data. So here's an example of so-called squared loss function, where we take the God label. So this is from the data set. These are the God labels. And for each of them, so we're iterating over the data set, for each of them we take the true value and the difference between true value and what we're predicting by our model. So this is the function of our model. And we want to make it positive, so we take the square. And we take the average over all examples. So this is the average loss function over the training data. We'll get to the details later, but to sum up, we have some data points, we have a model, and we have a loss function. Now, having these, the goal of learning is to find parameters, so find such parameters that make the loss as small as possible, that minimize the loss. So we want to fit our training data somehow better. The better, the merrier. Of course, it comes with a difficulty, because if we have a really powerful model, it's possible that our model somehow actually just remembers the training data perfectly. So we can get a loss which is 0. And well, this is fine, because this is our goal, what we want to do. But maybe it's not really what we want to gain from the learning. So one part of learning is also to generalize to something we haven't seen before. Not only to remember everything we can learn from the training data, but also to being able to, in new situations, to do something that makes sense in this situation. And this is exactly what generalization is describing. So the goal of machine learning is not to minimize the loss function on training data. We want to learn something that we are able to generalize well on previously unseen data. So we're learning from experience, but the experience never repeats itself. There's coming new experiences, but we'll be able to act in these new experiences we've never seen before. This is something which we as humans can do more or less well, depending on the situation, but machines might be struggling with. So the goal of machine learning is to learn the task so we can perform something we haven't seen before. How do we going to evaluate the generalization capabilities of our models? So for example, we split our data set into 2 parts, training and test set. And while we're training on the training set, we want our models to perform well on the test set, and the test data are just hidden during training. So we never seen this test data before. This is our proxy to something like behave on previously unseen data. We can also prevent overfitting, which means that our model just learns the training data that well that it can't generalize well on the test data. We can prevent this by maybe putting some constraints on our model, or more concretely on the parameters. So for example, we might want our model to learn the object, to minimize the objective functions, to learn the parameters, but we want maybe to have the parameters very small values, or we can penalize some extreme values of these parameters, for example. And also by training so-called hyperparameters. So what could be hyperparameters? It could be maybe the number of hidden layers. It could be the learning rate. So learning rate, we haven't talked about it, but it's something which is important for the training. So number of steps maybe, or early stopping, or size of the batches, which is how many examples we learn at once, and so on. So these things can be estimated on some portion of the training data, which we call development set. We will come exactly to that later on, but there's just a simple overview of that overfitting is unwanted. We want to prevent overfitting, and we can either regularize our parameters, or we can tune our hyperparameters on some development data set. So what are the basics of machine learning models? We have 3 major components that make it work together in a machine learning system. So we have the data, we have the models, and we have the learning procedure. So here's the training data again. So there's a set of tuples where we have the feature vector and or input representation and the labels. And we will use n as the number of examples in the dataset. And there will be indexed by low case, by n, as a nth example will have n. And each input is some like d-dimensional vector of real numbers and we can call them features or attributes or covariates. So we have seen with the dog and cat example, features on 2 dimensions, but these could be different ones. The main thing to remember is that in NLP, we're working with text, so we need somehow to translate text into features somehow, because all the machine learning algorithms, they need real vectored features. Real valued vector features, so we don't have it as a text. And the same for the labels, so they have to be real numbers as well. And we might also use some notation for the representation of the entire input data set as a matrix X. So remember, if we have n examples in the data set and times d features, so X would be then a matrix where each row would be an example, and they would have dimension d. Capital D, yes. And here's another terminology, a predictor, or for a model, we call it a predictor, which is a function that when given a particular input, example, it produces an output. So we already talked about models as functions, and this is how this is what we call a predictor. So predictor is a function from the feature space. So these are D features, as we had before, D features. And the output is some real number, typically. This is for illustration, just a single real value. We, of course, might want to predict something which is more complicated, just a single number, which could be maybe a probability distribution over some classes. So then we would have our predictor would be a function from the vector space, from the feature vector space to a to the vector space of the dimension of number of the classes which we have. And we have now an example right here. So in classification, we want to predict some class from multiple classes, for example. So let's have 3 classes here for document classification. So let's say you want to classify our document into one of these. So it's either politics, business, or sport. And then our prediction would be into a vector of size 1, 2, 3. So vector of 3. And since this should be a probability distribution, then it must sum up to 1. Okay, so our predictor is from a feature space to the space of number of the cardinality of the set, basically. And we want to predict probability distribution over these categories. So learning is finding the parameters. The goal of learning is to find a model with the parameters, so to fit some training data, and such that the resulting predictor will perform well on unseen data. There's no surprise in that, I'm just repeating the same thing. Conceptually, there are 3 phases when we discuss machine learning algorithms. So far we were talking about training or parameter estimation. There is another one. When we have the trained model, we want to do something called prediction or inference, which means in a real time, we already have learned something. The model is capable of doing prediction on unseen data, and this is what we call prediction or inference. And there's another part where which we also a little bit talked about, is the hyperparameter tuning or model selection. So for example, this could be number of hidden layers or early stopping while learning. So these are 3 different phases. Now, since we know that our goal is to find good parameters of our model, so here's again described the supervised learning data set. So these are our labeled data sets or examples, and we want to estimate parameters of our predictor so that we want to find some good parameters that we can fit the data well. So we want to find such parameters that the output of the function will be very similar to the goal data. So, well, we won't perhaps learn a function that exactly predicts the training data, but it should be somehow very close to that. How are we going to do that is to define some loss function of the training data. So loss function for the training data, it means, how well are we fitting the data. So the loss function as L has two parameters, the true label and the output of the predictor. The N is the nth example in the training data. So this function has this input and it predicts a real number, a positive real number mostly, which we call the loss. And it represents just how big the error is, how big error we did on this particular nth example. And our goal then is to find a good parameter of the model theta star is that we minimize this loss across all the n training examples. We have a special name for saying that, minimizing over all training examples. But there is one assumption we have to take into account, and it is that our examples in the training data set are independent and identically distributed, IID. So it means that example 1 in the training data set has nothing to do with example 2 or example 3. So, they're just independent. Of course, it's not really always the case, but we have to, these are modeling assumption and we treat them as they are. So they don't interfere with each other. They do not statistically depend on each other. So these are IID. And then we are minimizing the so-called empirical risk or empirical mean of the loss over the training data. So remember, we have a loss for each of the example, the loss function taking the gold standard label and the prediction of the model, and we just sum them up and divide by the number of the training examples. So for each we compute a loss and just take the average. And this is what we call empirical risk. So empirical risk is a function of our predictor, the input data set, and the input features and the input labels. So one example we've seen already is the squared loss, where our loss function is defined as just a difference between the true label and the predicted label, and we take the square of that difference. Why the square could be important here? Or is it, does it make any sense? Like really could be just, up to 4, it could be an absolute value and so on. So there are some implications. One is that it's easy to make a derivations of this function. And second, it sort of penalizes very large differences. So if the difference is very large, it gets the loss gets larger, for these differences. So it gets much more penalized, and it will push the learning towards, avoiding these large differences or these huge losses. And minimizing the empirical risk using squared loss is taking the loss function for each example. So for each example in our data set, we take the difference of the square of the difference and take the average. And we want to minimize this empirical risk. However, minimizing empirical risk is fitting the training data well, but we are not interested in performing well on training data. As we said, we want to make a predictor that performs well on unseen test data. So formally, we're finding a predictor that minimizes the expected risk. So expected risk would be something that we would expect on all data sets, on overall. If we have all training example on the world, this would be our true expected risk. So this is why we call it true. Where y again is the label, and this is the prediction based on the example. So nothing new here. So we would take the loss of y and x. But here comes the expectation, and could be like, well, why is it expectation? I mean, expected value, what is it doing here? Do we have any probabilities and so on? So we'll come to that in the next slide in more detail. So here we have again the formula of the expected risk. So it's expected risk over our loss, which is the gold standard, and the prediction. And the loss could be anything. It could be the square losses we just saw, or any other loss. But now we're extending the expectation here. So expectation has something to do with probability distributions. So we take the x and y's are they have some probability distribution, some joint probability distribution. How can we understand it? For example, we can model our world of all examples as a joint probability distribution of the features and the labels. And we don't know actually this distribution. That's the issue. We don't really know, because if we want to compute this expectation, so we would take from the definition of expected value, it is the function here times the probability, and taking a sum or integral. So this is the function times the probability, and over all domain of the probability distribution. But this is problematic because we don't know, we don't know the true distribution of our labels and the examples. We don't know this. So it comes, theoretically we are interested in the true expected risk, but we cannot do that because we don't know, we cannot compute this integral, we cannot compute this expectation because we don't know the probability distribution of all data sets and all gold labels. So the question comes, how to estimate the expected risk from finite data, so finite data, and how can we still make something which generalizes well. So we turn empirical risk minimization into minimizing expected risk approximately. And how do we do that? We simulate the unseen data. So we take out a part of the labeled data and we say, well, this is unseen data we've never seen before, and this is where we test our generalization. It's I hope it's not confusing, because it's just mathematically formalizing what we are somehow using common sense, what we are doing anyway. But behind that there is a statistical learning theory which really says that, well, if you take an average of the loss, if your data set is large enough, you will converge to something which is the true risk. And there's some in the statistical learning theory. There is also some guarantees on the bounds, how big your data set has to be to achieve some error in some neighborhood of the true error, and so on. So to do so, to really test our generalization capabilities, we always split our data into the training set, where we use to fit a model to learn the parameters, and to the test set, where we evaluate our generalization performance. And this test set, never ever look at test set whenever you are training your machine learning algorithms. Never do that, please. Never. People do that. So why? How they do that? So the point is, once you touch your test data and then tweak your training a little bit, you're cheating somehow already, because even if you are just once evaluating your test set and it's like, maybe I could do something better here, maybe better hyperparameters or whatever, then you break this rule of never seen, because you saw that. And it could be unintentional as well. And so, for example, there are several data sets that have been used for a long period of time in NLP for example, part of speech tagging. And the data set is already split into, so let's say, part of speech, and it's split already by the authors into train, def, and test. We haven't talked about the def that much, but training and test is clear. Which means every researcher comes with the same setup. And it's known, everything is known here. And we train our model here, and then we look at tests, and the next researcher comes, and so on. So the test data somehow became part of this whole life cycle, which means we're not really saying our true generalization capabilities when training them, doing research on this data set for 20 years. We're just better fine-tuning to this particular test set, but not really learning that much better on part of speech tagging. So this is hard because having a large collected data sets with labels could be costly, and you don't want to do it again and again. But you have to pay attention to when you really evaluate your algorithms, on which part of data is it really unknown or not. We are having shared task in this in this lecture, and the shared task tries to actually do that by hiding the test set completely. So it means you will have access only to training and maybe dev data, but you will never see the test data. You will submit your system or predictions on the test data, but you cannot fine tune that much. So it's really hiding the test data is one way of finding the true generalization error of the system. So the empirical risk minimization can lead to overfitting because it's just fitting the training data because it fits too closely to the training data and doesn't generalize well. So having very small average loss on the training set, but a large average loss on the test set. Yeah, so it happens when we have very complex hypothesis class, this very hard problem and very little data. So we're fitting well our training set, but we are pretty bad on our test set. So it doesn't really generalize. We overfit it. We learned that much on the training set. It's a complex thing, and we had a complex model to fitting easy problem, and it doesn't generalize. A very popular technique for estimating generalization, if you have limited data, which is almost always, is cross-validation, and in particular k-fold cross-validation, which takes the data and splits that into several subset chunks, and some of them are used for training, while the remaining one is the validation set or test set. And it's pretty straightforward actually. So now we have an example of 5-fold cross-validation, which in the first fold, it splits into 5 different chunks, and the first fold it takes 4 of them to train and test on the remaining one, and it repeats 5 times, and which means we always testing on the different data set, but at the end of the day we used all the data for training as well all the data for testing. So in detail for each of these partitions, the training data for this partition creates a different predictor, so it's specific to the k-fold, and then it applies to the validation set of the k-fold, where we compute the empirical risk for this particular fold. And we approximated the expected error by taking the average over all folds. So we take basically, we call it expectation, but it's basically an average of the empirical risks for each of the folds. And one extra point in cross-validation, or one extra approach, is nested cross-validation, when we want to also hypertune our parameters. So remember, we have this train, def, and test data given. Well, maybe we don't want to do that. Maybe we want to make it to use really all data for testing on, as we had in cross-validation. So in that we had nested cross-validation. So here's again a fold from cross-validation, so the k fold, where we split up into 5 parts. This will be our test for the fold k, and then we would do an inner loop here over these 4 folds, where we would take the 3 remaining folds for training, and this one would be a validation fold for tuning our, for example, hyperparameters. And then we would find the best hyperparameter on this validation set for this fold, and then we would test on this test fold as in typical cross-validation. Which brings me to the evaluation of our systems. So in classification, we typically use accuracy on the test set. So we're learning some loss function, but a loss function and evaluation function could be different things, and they typically are, because we're learning with, for example, the square loss or some other losses, which we'll go to that later. But for evaluation, we're interested in maybe the classification accuracies. So for example, accuracy is how many instances are correctly classified divided by the number of instances overall. So if you say accuracy, you somehow also understand this is like how many of them did I get correctly. There could be other evaluation measures. So if we have a continuous output, we can look at maybe correlation. If we have sequence, we can have a look at edit distance. But we have other metrics for NLP, particularly for evaluating maybe language generation. So we'll get to that later. But now here's an interesting example for how accuracy could be or could not be really useful for evaluating a system. So let's say we have two systems. So we have system A and system B. And they both evaluate whether a patient has a rare disease Q. And we want to compare these two systems, so like which system is a better one. And we have something called a confusion matrix here. So confusion matrix, where it's 2 times 2 matrix and saying like just the counts in the data set, how many times the patient has the disease and the prediction was that it has a disease, or patient has disease and the prediction was wrong. Prediction said like, oh, it doesn't have a disease, and vice versa. So it's just basically counting the instances which were correctly classified, or they made an error and which type of error was made. So if you look at this, and if you look at accuracy, so accuracy is the number of the matches. So if we say he has a disease and we said he has a disease and the patient had disease, so this is the number, and which he hasn't disease and the prediction was also correct. So the correct one, so this is diagonal basically in this confusion matrix, is for accuracy. And we will compute this accuracy as a 0 plus 1004 over the number of instances, which is 1000 and something 15, yes. So the accuracy here would be 0.99. And here again, so we just sum up the diagonal. So it's again 1004 over 1015. So both these systems have accuracy of 99%. And you might be asking, okay, but there are some differences. I mean, these are not the same. Just look at this. This couldn't even predict nothing where it was a rare disease, but it always said like for the disease it said no disease. While this one, it did something. So accuracy is not really telling these differences in misprediction of different kinds. So we have to have better techniques for that. Let's create a terminology for that. So the confusion matrix, as I said, for binary classification, had something is 2 times 2 matrix with true positives, false negatives, false positives, and false negatives. It's used everywhere, not only in machine learning. If you look at a PCR test for COVID-19, you will see this. For evaluating tests, for medical tests, is the same thing. So you might remember it as like that. So okay, true positive is it was true. It's a true and it was positive. If it's false negative, it means the system said negative and it was false. The system said it's negative, but it was wrong. For false positives, the system said it's positive, but it wasn't. And for false negative, it said, it was negative and it was actually false. So, sometimes it's better to look it up in Wikipedia, I have to say. But that's, if you make these numbers correct, then everything else which follows is correct. So for the class disease, if the system B has a precision of 4 over 9. So I'm coming back. We have 4 and over 9. So the precision is on the column here. And the recall was 4/10, which was 40. And system A has a precision of 0 and recall of 0. Okay, so if you compared it for the class disease, then system B is better than the other because all two metrics, precision and recall, are better. You can do it also for class no disease, and here both systems are very close. So the precision and recall for class true disease and no disease, they have different names and different setups. So you can see sensitivity and specificity, or precision recall and so on. And there is a long list on Wikipedia. I suggest you just to look it up, and they're all based on counting true positives, true negatives, false positives, false negatives. They have different names. If you want just a single number, then we are typically using something called F measure or F1 score. So F measure or F1 score. And it's taking both precision and recall. For computing the F score, it's a harmonic mean. It takes 2 times precision times recall over precision plus recall for each class. So if you have more than 2 classes, then precision and recall are defined as. So precision for class K is the number of the matches. So this is from the diagonal. And then we are summing up precision over row. Is correct? Yes, I guess so. And the recall, we are summing up over the column. So if we look at it again, so say we have 3 matrix like 3 times 3, and we are interested in so 1, 2, 3, 1, 2, 3. And we are interested in precision of this. So we are taking this would be the denominator. So this goes here, and now we're summing up over all rows. Yes, so we're taking this sum, and this will be our denominator, right? So on the columns is precision, and recall is summing up the row. And if you have multiple classes and we are interested in one single measure, one single F1 score, we can either compute the F1 score for each class and then maybe average over scores. Or we can do, or we can first compute precision and recall average and then get a score. So there are different ways of doing that. And if you really want to make sure that you're doing if you really want to make sure that everybody understands what you're doing, then maybe like this could be a good reference because they're all explained. So if you say like, okay, I'm doing macro F1 score inside this article, then it's very nice overview. And also there's some caveats of computing different macro and micro F1 scores and precision and recalls. So this is a beautiful article, apples to apples in cross-validation studies. So how F1 score and cross-validation, how do you do that exactly, can impact the overall score you're reporting. Well, it's all good and nice if you would all talk about accuracy, but in NLP, and especially in language generation, evaluation is far from being trivial, because in language generation, we are not just classifying things into apples and oranges and just counting the numbers when we hit the match or not, but we're generating language, and it makes it super complicated to do it well. So there are some measures for evaluating language. In machine translation, there is this very famous score called BLEU, and it's based on n-gram matches between the candidate and the reference. So the reference is something which you're given as a gold standard data, and the candidate is what you're generating basically by your system or translating in your system. And you're computing the overlap or it's based on the overlap of word tuples, so n-grams. But increasing the BLEU score is not always an indication that you're improving the quality. So if you're optimizing only for BLEU score, and you're getting better and better, it doesn't have to correlate with human perception that you are doing any better. So you're optimizing a metric, but not maybe what humans see as a performance improvement. And the same for summarization. So Rouge L, it seems like they have French names, all of them. I don't know why. So Rouge L is the longest common subsequence between the candidate and references. So again, it's based on the shared words, but here in Rouge, they don't have to be even continuous. So, and if you want to read more, this is a recent paper from Colling, Curious Cases of Language Generation Evaluation Metrics, and they have some beautiful examples how it can fail. So you want to may have a look into that. So we're coming to the next part of this lecture. We're leaving evaluation and we're moving to loss function. So from something at the end to something in the core of training our algorithms. And we already seen one example of loss function. So let's have a closer look again. So we already introduced the loss function as a function from of two parameters, real values, which produces a positive real value. So again, the loss is based on the true label and the predictor's output, and we're getting the so-called loss here. If we have multidimensional output of our neural network, so for example, if we have m output neurons, we can simply extend our loss function to produce multidimensional vectors. So this would be, the input will be multidimensional. So the input will be two vectors here, and again it still outputs one single real value, the loss, and we'll change simply the true label to the true label vector and predictor vector. And we have this n for denoting nth example in the training data set. But if this is clear from the context, we will just simply write the vector without the n, because it's very cumbersome here. The vector is yn1, yn2, and so on. So we'll just use, this would be the vector of m inputs for the loss. So we already had a square loss, which was simply the distance squared. And for multiple dimensions, it's very easy extension. So we just subtract these two vectors and take the square, which means for each of the position here, we take the square. And as I said, we're dropping the n here for the nth example. Now, before coming to the next loss, we should spend a slide at least on one concept for comparing or measuring distance between two distributions, so between two probability distributions. It's a distant metric. It's not a it's a distant measure, not the distance metric. So metric needs to be symmetric and triangle inequality and so on, but we don't have it here. It's just a measure. So Kale Divergence, perhaps you know it, perhaps you don't. It's also known as a relative entropy. And it goes like that. It's the idea is why, motivation, why should we do that? So imagine you have two distributions, and I can paint distributions as a simple histogram. So we have, here one histogram, like that, and 1, 2, 3, 4, 5, 6, 7, 7 categories, and here would be another, again with 7 categories, and like that. So, for example, so assuming these have the same, the same categories, or the same cardinality of the spaces, or the same meaning of these random variables. So let's have y and y hat categorical random variables over the same categories. So they would have, this would be like 7, and this would be also 7 in this example. And we want to measure how, the distance between two probability distributions. How far is this from this? And you can do it in many ways. You can take like maybe the maximum difference, or you can take some average, and you can take something which is more information theory based. And this is exactly the case of Kale Divergence. So Kale Divergence is trying to, it's a Kullback-Leber divergence. And it's trying to measure the divergence between two probability distributions. And it goes like, the definition is its expectation of the logarithm. So the logarithm is base 2. We mean it's base 2 because we measure in bits. And we take the logarithm of the ratio of py over py hat. So this is the definition of Kale divergence. And if we work it a little bit now in detail, like some algebraic operations, we'll get to something which will have some effect later on. So this is from the definition. Now, how can we go from here to here? It's from linearity of expectations. So expectation is a linear operator. So we can do, oh, sorry, not yet. Actually, like logarithm of a fraction is subtracting the logarithms. So we'll simply get this. And now, since expectation is a linear operation, so we split this into two expectations, right? So far, should be no surprise. Now, we will change here this into logarithm. So we make a fraction, so to -1, and we put a minus in the in front of this expectation, and we keep the second term unchanged. And this is a definition of entropy of random variable y according to probability distribution p. So this is entropy of py, and we're having two terms here. Okay, so it's a little bit of algebraic operations and so on, but it will turn out to be useful in the next slide, because we're using something called cross entropy loss, and here where the entropy comes into place. So this was the result of literally playing around with Kale divergence. So we ended up with the entropy of y minus expectation over this function. And this is a loss. So we're trying to minimize, we're measuring the distance between the true labels and the predicted labels. As we see here, this term, this entropy of y, it doesn't depend on the predictions. So if we want to minimize this divergence, we are not interested in minimizing this because this will remain the same. This is coming from the gold standard data. We cannot do anything about it. This is given, right? So we are actually interested only in minimizing this expectation, right? And we can just work it a little bit more from, okay, so let's define the loss as this term, right? So let's take this and put it here. So our cross entropy loss is this term. It's minus expectation of this logarithm of the predictions. And now, well, how can we turn it into, well, we have probability distributions, and then we have vectors of predictions. So we turn basically, we say that probability of being in a vector is just okay. Let me give an example. So let's have a y vector here. So this is y vector, and we're saying that probability of y being here is just the number in the vector. So, right, the vector is a probability distribution, so we say, okay, well, being this is basically the value in the vector. So now, from the definition of expectation, is it's a function times a probability distribution for each, and summing up for all values from the random variable. So now we have it as a probability of y being m times the function within, the logarithm py is m, which basically ends up with this summation. So this is our cross entropy loss. It's measuring the difference between the true label and the logarithm of the prediction, right? And you may only remember this. This is fine, you know, just how you compute that. But it has a meaning. So the meaning comes from the Kale Divergence. And also, if you minimize this to 0, well, okay, it has a minimum, and the minimum will be equal to the entropy of y. So let's compute some examples. Let's have again yn is some example true label, and y hat is the prediction of our predictor. So for example, this is our true label, so a vector of 0, 1, 0, 0, and these are our predictions. So taking the formula of cross entropy loss is basically saying I take the gold standard times logarithm base 2 of the prediction and summing up. So for example, here I'll go through both vectors. So 0 times anything is 0, 1 times 3 is 0.3 is 0.3, and then 2 zeros. So I'll end up with a logarithm of 0.3 and minus, and this is this number. If we take square loss of the same predictions, so we take basically all of them. So square loss is again 0, 0 minus 0.25 squared, 1 minus 0.3 squared, 0 minus 0.4 squared, and 0 minus 0 point squared. And it's a number, I don't know, I didn't compute that, but you can compute it easily. So it's a different number. So, you know, we can see that the cross entropy behaves differently because it ignores everything which is 0 in the gold standard data, while the square loss computes all of these differences. And we might also have a look on how strict the cross entropy loss is. So here's one example, a very simple one. So let's have y of being just 1 and 0. So this is the gold standard. And now let's have a function for predicting y hat n. So being a predictor. In the previous example, we had, I'm coming back now. In the previous example, we have these given, you know, so we have this gold standard and these were also given. But here we want to make them somehow as a function of something. So these examples would be maybe, so we take z from 0 to 1. So it would be maybe 0, 1, and, you know, 0.1, 0.9 or 0.5, 0.5, and up to 1 and 0, right? So we're taking z as from 1 to 0, and these will be different y hats. So if we put it into square loss, there's a function. So if you do some algebra around it, you will get this function. And it looks like that. So for increasing z, the square loss for this particular example and this particular example parameterized by z will look like that. So what does it mean being here? So if z is 0, our prediction is this, is 0, 1, right? So 0 and 1. So our true label is 1, 0. So this is like very far away and should be penalized. And of course it is penalized more than being here, which would be 0, 5, 0, 5. So 0, 5, 0, 5 versus 1 and 0. Yeah, it's closer than 0, 1, but not much. So we're penalizing worse predictions. That's correct. However, if we use the cross entropy loss, then after doing some algebra, well, it's basically minus logarithm of z. And if we plot the minus logarithm of z, we see that, okay, for, you know, some middle values like 0.5, 0.5, so if we compare 0.5, 0.5 to this, it gets penalized somehow. But the worse we're getting, the bigger the losses, and it's drastically, it's basically exponent, it's a logarithm, a negative logarithm. So it can't be ever zero. So it's like we're penalizing very badly. And so, for example, if we have 0.01 and 0.99 would be our prediction, then we would be somewhere here, because z is 0.01, and the penalty, the loss is super huge. It goes to infinity basically here. So cross entropy loss is basically penalizing bad predictions very high, while square loss, it's somehow okay. It's worse, but not that bad. So cross entropy loss is really pushing hard to be closer and closer, and bad predictions are really penalized. Okay, it brings me to the summary. So in today's lecture, we had this bread and butter of machine learning. So we're talking about some notation, why it could be confusing, vectors, matrices, and so on. And we talked about the goals of supervised machine learning. We touched the topic of generalization and overfitting and why it's important to do cross-validation or even nested cross-validation. We talked about different evaluation scenarios such as accuracy or other in machine learning and natural language generation. And we are talking quite a deep about different loss functions, namely about two, which are the mostly used losses in NLP and machine learning, being it cross entropy loss or the square loss. So thanks for watching, and next lecture will be presented by my colleague Dr. Mohsen Mesgar, and he's going to talk, I guess, about backpropagation. So stay tuned. Thank you.